is the second problem for homework 15. We have this doohickey, and it's called a crank slider. This thing cranks and this thing slides, and it's cranking at 20 RPM counterclockwise as shown. The dimensions are 200 millimeters, 150 millimeters, and 230 millimeters. And I think I got those right. Using the methods shown in class that require diagrams, determine the acceleration of points B and D. So I call it a 3-diagram method, but not all the professors do. So here I've drawn this thing out, repeated here, and we'll start off with a velocity analysis. I didn't ask you for the velocities at every place, but we do need to do a velocity analysis. So we start off with doing a velocity. I could do a velocity and acceleration analysis of link AB. So it's going to have a velocity right here, the velocity of B, right there, right? And this is going to be omega AB right here. There's also going to be an acceleration. I should do that one right there. So we're going to have an acceleration of B is going to be the acceleration of B in the normal direction, which is omega AB squared times LAB. I also should say that the velocity here, I should have wrote that up, speed really. So we end up with, we need to turn RPM into radians per second. So 20 rev per min times 2 pi rads per rev divided by 60 seconds per min gives us 20 I guess, okay, 2.094 radians per second. And I got in the way of this thing. Boop. I'll write it down below. No, I could put it like I can make it fit. And 200. So 418.9 millimeters per second. Damn, really squeezed that in there, didn't I? So 2.094 squared times our 200 and 2.094 squared 200, boom. And we have 877.0 millimeters per second squared. Okay, now we do the velocity analysis of link. I'm going to call it BCD, but it's not the right order. I'll go DBC. Okay. Link right here. Now, one aspect is the velocity. It has to be horizontal here. So what we end up finding here is that this right here is the velocity of B. And, whoops, right here, since we have to keep going in a horizontal direction, our conclusion is the velocity of c. Like one way that we could do this, I think this is convincing, is we could draw. It says no ICR, therefore pure translation. VB equals VC omega. I don't like calling it DBC, but that's the order I didn't. Okay. So I'll move it down to the next thing, to the acceleration analysis. And I didn't leave myself a lot of room, but maybe I'll do it over here. See, I will make a little light sketch right there and put a little line right in there. And then when I move the thing over, like that. There you go. So here is our all right, so we're going to put in our acceleration that we know. That's our acceleration of B. Here's one that we don't know, but we do know its direction. So we're going to put it into both of them. Acceleration of B. Acceleration of B, and then we're going to pin it and write out its direction for the tangential one, and it has none in the normal direction. So I'll write that somewhere. Let's see, another thing I needed somewhere was some geometry. Would have been good to do that in the beginning, right up here. So let's put that right up in here and say theta. So we say that theta is equal to sine, yes, inverse sine of rise 200 over hypotenuse 230. So 200, 230 divided inverse sine, 60.41. 60.41 degrees right there. Okay, so here is that angle right there. And what you can decide is that this thing is coming down, so this one must come upwards. So it must have an alpha of, what did I say, DBC. I like alphabetical order better than that. Okay, and so this is the acceleration of C with respect to B in the tangential direction. And noteworthy, acceleration of C with respect to B in the normal direction is equal to 0. And that's our theta right there. Yes. Okay. So, knowing that in mind, this is actually going to be, yeah, so that had to be upwards to counteract this. And therefore, what we're going to find is we're actually going to have an acceleration of C that goes in that direction. Interesting. Okay, so we write out the acceleration of C is equal to the acceleration of B times the plus the acceleration of C with respect to B tangentially plus acceleration of C with respect to B in the normal direction. Okay, so let's start in the y direction. In the y direction, it should be equal to 0. And then we're going to have a negative 877.0. And then we're going to have a positive alpha dBc times the length from here to here, which is 230, times the sine, the sine of 60.41. Alpha dBc ends up equaling, my keyboard gets in the way when I do this. My desk is getting smaller. I don't know why. Let's get more and more junk on it. Okay, I take the sine of that, and it's already in the Q, so I could just divide by 230, and we have 4.385 radians per second squared. And then in the x direction, we have the entirety of AC. We have nothing going on right here. I'll even put a 0 in there. And I probably even should have put a 0 right in here too, right there, just to represent this guy. So now, this is going entirely positive and is going to be 4.385 times 230 times the cosine of 60.41 plus 0. And so the acceleration of C is going to be 230 times that, and then 60.41 cosine times, so we get 498.0 millimeters per second squared. Right? Right, so that's the first thing that we wanted to do. But now let's do the other diagram. Now, we could have combined this onto one. I find that to be just trouble waiting to happen. So get another piece of paper. We'll make more. And write this thing out again. And I'm gonna cheat. Well, it's not cheating. It's just doing the right thing, right? So make a couple lines right in here, just to. Right here. Okay. So something like this. That might be a little steep. What are you gonna do? Okay. Equals plus, and once again, let's use the one that we that's right here. Let's go down straight, and what I like to do is when I don't know the direction, not 100% for sure, I choose it to be positive. So I'm going to take A D X and A D Y, like right there. Here is my A, B. And so I'm going to plug this right in there and right in there. So it's pure translation. So that's A, B taking place right here. And now I have pinned right here, but and we already established it was counterclockwise. I mean, we already know this alpha DBC. So we know that this has to be coming downwards like that and over to the left, right? And by the way, we know that's, do we know that? I think I made a mistake with my angle. I did make a mistake with my angle. Horse hockey. This right here is theta. So, this right here is theta. You could always, like, what you could do is you could like pretend like this is right here and just rotate this and wait, did that go right? Yeah. So this one closes up and that one closes up, so you know it's the same one. So shoot. Well, mostly what that's going to do is turn this into cosine and this into sine. And that's going to be different now. And that's going to be different. Well, it's good I recognized it before the end of the video. Then I would have to put this little embarrassing little mea culpa on top of the thing. And so I'm going to double check this. Okay. This is going to be in the y direction, so it's the cosine. All right. So we have 877 divided by 230 and 60.41, and take the cosine and divide it. All right, so what I'm left with is 7.722, right? And 7.722 and sine. So 230 times that and 60.41 sine that times, and I'm left with 1,544. Let's hope I didn't make any other mistakes, but that would be just way too wishful thinking. But, you know, making this thing, it's a good experience. It's good to know that you may, you know. So, I don't know what I just said. Just some, like, words. Word salad. So here is this angle right in there. And I guess what I would say here is that this is that angle. So, didn't make a really good job of this diagram here. Oh, and it's kind of smudged. It's getting smudged. Okay, let's try to recover some of your dignity. Okay, so right in there, and I think what we could say is that that angle right there is going to be my theta. This is going to be my, I just put a V in there. I'm tired. It's almost 10 o'clock. I got to go home soon. Oh, I got to make another video too. Ooh, shoot. This is D with respect to B. Tangential. And maybe I'll write D with respect to B, and the normal direction is equal to 0. And let's let's see what else happens here. Okay. So I'm going to write my a main equation here. D with respect to B tangential plus D with respect to B normal. And so in the x direction, I just write ADX is equal to 0 right here. And then we're going to have what's that distance right there? It's 150 millimeters between here and here. Okay, and that's negative. Let's write negative. Let's make it negative. That's usually I do keep it out to the outside. Okay, negative, and we have alpha of 7.722, and we have 150. But now it's going to be the sine of that angle, 60.41. Yep. So AD in the x direction is negative. We learned that. 7.722, 150 times 60.41 sine, and I get a negative 1,007 millimeters per second squared. And then we go into the y direction. ADY is going to be equal to a negative 877. It's going down. And then this one is also going down. It's going to be negative 7.722, 150, and now it's going to be, yes, going down. Okay, the cosine, yep, of 60.41. So ADY, all going to be negative number 2. 877, 7.722, 150 times 60.41 cosine times, and add them together, and you get a negative 1,449 millimeters per second squared. So the acceleration, we could write it out in a couple ways. I prefer to write out a magnitude and direction anytime I can. So I get 1007 squared plus 1449 squared. And they're still in my calculator that way. So squared plus square root. And we get 1,765 millimeters per second squared. And the theta of the acceleration of D, sometimes I write it out this way right there, is going to be the inverse tan of rise over run, or 1449 over 1007. Looks like I put a comma in the wrong spot. Getting tired. Probably made some mistakes. 1449 and 1007 divided, and take the inverse tan, and I get 55.20 degrees. So answers. The acceleration of C is equal to, did I decide? Yeah, it is going to be 1,544 millimeters per second squared, and it's going that way. Whereas the acceleration of D is 1,765 millimeters per second squared, and it is coming down that way right there at 55.20 degrees. I wish I had something to check this against, but I'm sure it has the potential of mistakes somewhere in there, but we'll see. All right, thank you, and I'm going to go do some statics, and then I'm going to go home. Another 25 minutes.